Yes, sir.
Okay. So first of all, I am very much thankful, uh, Dr. Manmohan, that you have accepted invitation to deliver a talk in 6 days online faculty development program on clean energy and environment sustainability, sponsored by AICT Training and Learning. It is my proud privilege to introduce Dr. Manmohan. Dr. Manmohan is a distinguished researcher in the field of hydrogen storage and thermal energy storage systems. Dr. Manmohan is currently a postdoctoral researcher at the University of Suwon, South Korea, and he is also associated with Ajao University, Korea. He earned his PhD from Vellore Institute of Technology, Vellore, India, and possesses extensive expertise in metal hydride-based hydrogen storage technologies. Presently, he is engaged in a Korean government-funded research project, National Research Foundation, focusing on the development of multifunctional phase change material. His research interest include the synthesis and characterization of carbon-enhanced phase change materials and the development of thermal energy storage systems utilizing phase change materials. Uh, He has made significant contribution to the field with approximately 25 research publications in very high impact factor journals, including papers in the top 1.5% of JCR ranked journals in energy storage. Additionally, he has edited a book, holds 4 Indian patents, and he has citations, Google Scholar citations by about 1,000. Dr. Manmohan have research collaboration with leading Indian institutions, including NITs, and it is my privilege that we both, me and Dr. Manmohan, we are working together also. And I request all the participants that whatever doubt you have, if you find, please ask and make this session very interactive. We are open for any collaboration in future also. If anyone wants to ask any question with me or Dr. Manmohan, we are always welcome. So again, I am very much thankful to Dr. Manmohan, and I welcome you, sir. Over to you, sir.
Thank you, Dr. Abhishek, sir. And I think the slide is visible, right?
Yes, visible.
Okay. So good evening, all the participants once again. So before starting this presentation, I wish to extend my sincere thanks to Dr. Abhishek and Dr. Murli Manohar for their constant update and seamless coordination, ensuring that well-organized, enriching experience, and the AICT sponsored FDP committee, they have given the opportunity to share my small research work so far what I did. So
Sorry for the interruption. I am doing me marking mute.
okay, no problem, sir, please. So I think okay. So
If you are
the
after means before starting the presentation, if you want to switch off your camera, you can do, sir.
okay, sir.
Okay, yes, sir.
So now the presentation, I think I should start. The topic is advanced nanotechnologies for multifunctional phase change material. So this is, I can say, this is the little advancement that Dr. Adarsh Kumar Pandey has been given in the previous talk, as I was there in the presentation. So I hope all you are also there. So in that time, Dr. Adarsh Pandey has given some presentation related to phase change material, but it was limited to the energy storage technology. So I think I am going little forward from the energy storage technology, although I will start the presentation with the energy storage technology, but after certain time I will change the track and I will go to the multifunctional application of the phase change materials. So as you can see, you can see in the slide the world energy scenario and the phase change material. So the slide is visible, sir? Vishek, sir?
Yes, sir. Visible, sir.
Okay, so in the slide you can see the energy gap between the energy supply and demand. So as you can see, the demand is continuously increasing after the year 2005 or 2010. There is a gap is starting between energy demand and supply, and this gap needs the development of sustainable energy clean sources. So as we know, there are many energy sources that are renewable, but among the renewable sources, the previous lecture also you have seen the solar energy can be considered as a promising energy carrier for the future. And also from the childhood we have seen there is one small, we can correlate, as I giving example, we can correlate this thing with the phase change material. So in the childhood we can see there was a one earthen pot. We used to collect the money when we have some excess money or someone giving certain money to us, then we are keeping and keep storing for future. When we need something, that time we can utilize that money. So this, in the same manner, PCM also store the energy when the energy is in abundant, like when the daytime or the sunny days, when the solar energy is in abundant, we can utilize that energy to store in the PCM. And when the energy source disappear or in the night time, we can utilize the same energy for our demands. So this, in this way we can correlate the world energy scenario and the phase change material is nothing. Phase change material is nothing, uh, is a medium to store the energy, so that when the demand rise we can utilize the energy. So in the continuation of the world energy scenario, we can see that was the fundamental of the energy storage material. If we'll go for the little technical in depth, we can see there is two type of energy: high grade energy and low grade energy. Okay, so low grade energy is what we need to utilize in the uh, real time application or domestic household application. So when we convert the high grade energy to low grade energy, like high grade energy is what? Electrical energy, chemical energy, kinetic energy, and nuclear mechanical energy. These are the high grade energy. But low grade energy is what? Directly heat, waste, radiant heat. And suppose we want to warm the water or we want to cook the food, these type of energy, that is called the low grade energy. So this thing already Dr. Adarsh Pandey has given in his talk. Then whenever we uh, convert the high grade energy to low grade energy, there is some losses. So in this way we can utilize the phase change material or the energy storage material. So in this presentation, throughout, sometime I will use the energy storage material or sometime I will use the word phase change material. Both are similar actually. Energy storage material, there are, it is a vast category. In that category, phase change material is one category. Okay, so please consider energy storage material or phase change material as a similar meaning. So as you can see in the figure, when the solar
हेलो।
energy, hello,
हाँ। अरे हाँ सर, नमस्ते नमस्ते, कैसे हैं सर? हाँ 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 हाँ।
okay. So whenever we are converting the solar energy through the photovoltaic modules, there is some losses. Nearly, as you can see, the efficiency of the collector is only 15 to 22%. So roughly we can say there is a losses of 80% in this case. So already we are getting loss of 80% when we are converting the solar energy to the electrical energy to store in the battery or some other medium. So already we are getting loss of 80%. If further we are converting that energy, electrical energy, to utilize for low grade energy, like if we are using electricity to heat the water or to cook the food, in that case also the joule losses will occur. Joule losses is nothing, it is when the electrical energy is utilized to convert it as a heat In that case, the joule losses will take place. In that case, also the efficiency is 80 to 95%. In this way, we are also again once again we are getting the loss of 15 to 10 to 15%. So in this way, we can see the losses. So what we can conclude from here, if we are converting high grade energy to low grade energy, there are several losses. To avoid these losses, what the PCM does, PCM can store the energy in low grade form only. Means PCM can store the energy as heat only, not in the electrical form. That means we are storing the solar energy in the form of heat, and further we are utilizing in the form of heat only. So there is no conversion of high grade energy. We are storing heat as a heat, and further we are using as a heat only. So there is no intermediate high grade energy conversion. So in this way, the end product we are utilizing what we are storing. So these in this way, the phase change materials comes in existence. Now, these are the scenario of phase change material. These were the scenario of the phase change material. Now, let's start with the fundamental. What is the phase change material and their type? So, the first I wish to introduce phase change material as a ice and water. In case of ice and water, everyone knows ice having three phase: solid, liquid, and vapor. So, in that case, we can see at certain temperature the water takes place as a solid, and at certain temperature the solid becomes water. In this way we can say ice and water is a phase change material. Similarly, paraffin wax in general we can say is a wax also. It is a phase change material. Generally we are using for the energy storage application, thermal energy application. You can see in the figure, wax is nothing like we are using to make it candles. That is the phase change material, or paraffin wax we can say. And also the salt hydrate. Salt hydrate are also the phase change material, but the melting temperature of these materials are little higher than the paraffin wax as well as the ice water combination. Further we will go about this phase change material, phase changing temperature. So in the middle figure also you can see how the phase change material takes heat and convert it phases, and how the heat transition takes place. So in the solid state, if we will rise the temperature, definitely it will change the phase and it will become liquid. And further, if the heat from the liquid phase will further takes place transfer to the surrounding or other medium, it will again change its phase and it will become solid. Now this was the fundamental of the phase change material and the scenario. Now we will go for the multifunctional PCM. So as literature says that in early days phase change material was only, or phase change material in short I can say PCM. Phase change material in early days, it was utilized only for the thermal energy storage. As the demand increases, as the material efficiency, cost effectiveness, compact design are come to existence, everyone goes towards the multifunctional things. So in this way, multifunctional PCM also come to the picture. When the material efficiency requires, multifunctional PCM combines multiple properties into single material. Further, in the next slide or upcoming slides, we will go what are the application. Through that, we can say PCM is a multifunctional material. So as of now, I only discuss the thermal energy storage. In later slide, I will go for their diverse application. Based on that, I will define multifunctional PCM. So now, as of now, I'm going only to the what is multifunctional PCM and why multifunctional PCM come to the picture. Further, when the cost effectiveness come to the picture, by integrating multifunctionality such as optothermal conversion or EMI shielding, if someone want to make such a material, it will all the function will come together in a single material. That is called a cost effectiveness. In such a way, the multifunctional PCM come to the picture. Further, compact design. someone want such a material, that a small quantity of material can perform multiple tasks. In that case also the design will become compact. In this way multifunctional PCM come to existence. Further, ease of handling and installation. If one material can perform multiple tasks, then the material handling will become easy and installation of the system will become easy.
Sorry, Dr. Manmohan. I am making him
Okay,
his
okay.
audience.
Okay, so material handling and installation will become easy in case of multifunctional PCM. So these are some basic things through that we can understand why the multifunctional PCM is needed. So in short, I can say to save money and to save the effort, we can design the multifunctional PCM, or we want to design the multifunctional PCM. These are some milestones that multifunctional PCM needs to incorporate to perform as a pure PCM to become the multifunctional PCM. These are the milestones through which the pure PCM has been designed as a multifunctional PCM. So it starts from the 1990 when the carbon nanotube has been dispersed to the phase change material. In this way, in 1990, the PCM has been started as a multifunctional PCM, and continuously the research has been going on. In the last, in you can see 2023, Dr. Adarsh Kumar Pandey's group has been developed a tetrapod like nano material through which they have obtained a multifunctionality or high grade performance of the phase change material. In between, many stages has been comes through which the researcher has been obtained different applications as well as the uh, uh, I can say good performance of the phase change material. In this uh, journey, the phase change material has been incorporated with different material. That material is from 0 dimension to 3 dimension. Like 0 dimension material, I can say carbon nanodots or carbon quantum dots, metal oxide particle in the nano size, 1D material that is carbon nanotube, carbon nanofiber, 2D material like graphene oxide. These are the 2D material that also has been tested for the phase change material to achieve multifunctionality, as well as the 3D material like carbon foam, carbon sponge. These are the journey of phase change material from 1990 to 2023, and still it's going on. I'm also trying to get some better result through incorporation of not only 1D, not only 2D, hybrid material. I'm trying to get the multifunctionality of the phase change material. So as I already told you, phase change material is nothing, it's a energy storage material by its changing of phase. Further, I will discuss more about the phase change material in upcoming 2-3 slides. So these are some type of phase change material, basically categorized into 3 types: organic, inorganic, and bio-based PCM. So organic PCM is the most common research material, I can say, because I gone through many publication. In most of the publication, I have seen organic PCM. Why? Because the organic PCM is easy available, some non-corrosive nature, and melting temperature is also suitable for the wide range of applications. The only disadvantage of most of the phase change material is their low thermal conductivity. Especially organic phase change material is having the disadvantage, that is its flammability. It's easy catch the fire. So this is disadvantage, but there are several advantage of organic phase change material. And the fundamental phase change material as a organic is a paraffin wax. And further, the organic phase change material is divided into 2 categories. That is, one is paraffinic and second one is a non-paraffinic. In paraffinic, it derives from the petroleum product, whereas non-paraffinic is a fatty acid, alcohol, ester, glycols. Like the most common example is stearic acid and lauric acid. whereas in the paraffinic, that is the paraffin wax. If we will compare these two, paraffinic and non-paraffinic, the advantage of non-paraffinic is high latent heat. Further, we will discuss what is the advantage of latent heat and thermal conductivity. Definitely, we will go for this because this lecture is basically for the thermophysical property and through the nanomaterials. So definitely, we will go for the latent heat. What is the importance of latent heat and thermal conductivity? The disadvantage is high cost. Non-paraffinic is little high cost than the paraffin's organic PCM, and also limited availability for some types, not for all non-paraffinic, but some special kind of paraffinic, non-paraffinic is not easily available. Now, if you will go for inorganic PCM, it comes only for salt hydrates. That is the sodium sulfate is the most common example, and calcium chloride hexahydrate is the common example of salt hydrate. The advantage is high latent heat as compared to organic. This inorganic is having high latent heat, non-flammable and cost effective. But the major disadvantage of inorganic is their corrosive nature. Why I can say is disadvantage, because when we design certain system that can store the solar energy in the form of heat, it definitely needs certain container. In that container, we have to fill the phase change material. In this case, this inorganic PCM will make corrode that container, and it will destroy the structure maybe in 10 year or 5 year. Whereas when we go with the organic PCM, as you can also observe this thing, if you will keep the paraffin wax, simply we can say a wax, uh, definitely you have seen this thing, it will not damage any metallic things. But in case of inorganic material, it will corrode the container. So this is the disadvantage of inorganic PCM. Now, bio-based PCM, these are the recently developed, not developed, recent research material. Uh, Basically, when we go for sustainability, in that case, the bio-based materials come to existence. So it is a recent research material like soy wax, palm oil, coconut oil. These are the bio-based phase change material. This type of material, when derived from the nature, so advantage, these are the eco-friendly, biodegradable and non-toxic. But the disadvantage, when you utilize these material for long time, certain uh, cyclic process, multiple time heating cooling, they will degrade their thermophysical property. So this is the disadvantage, termed as a limited thermal stability. So limited thermal stability means what? If you will utilize at high temperature, it will lose their properties, and also higher cost. So these are the some disadvantage of bio-based PCM. Now, as you can see in the picture, there is a plot. In that plot, you can see melting enthalpy and melting temperature. So I wish to introduce these two parameter, what is melting temperature and melting enthalpy. By the name itself, you can understand what is melting temperature. With the one example, I can say coconut oil. As you observe, in the summertime, the coconut oil is automatically melted, like 40 degree or 35 degree, it will melt. So that is the melting temperature of coconut oil. And also, what is the melting enthalpy? It's little bit complicated as compared to melting temperature. When certain material pick the heat, it will get melted. In this case, the material will hold certain energy. So the amount of heat when some material needs to change its phase, that is called a melting enthalpy. So these two parameters are very important to utilize any phase change material for any particular application. So in this way, I can say if the material is having high melting enthalpy, in that case, it can store more energy. Like if you will give heat to the coconut oil, it will melt easily as compared I will give some complicated chemical things. Maybe it will melt at more time or more temperature. So in that case, in general observation, what you can say, the coconut oil is easily melted. That means it can store less amount of heat. But some chemical materials like paraffin wax, or I can say some calcium chloride hexahydrate, it needs more time or more heat. That means to change its phase, it will store more amount of heat. So one material which is easily melted, it can hold less enthalpy. One material which is taking more heat to convert its phase means it can store large amount of heat. So better, what material is better for energy storage, which can store more amount of heat. So in this way, salt, you can see in the picture, salt is having big circle and the temperature range of melting is 300 to 400. And also you can see the melting enthalpy starts from 200 and it goes over around 700 megajoule per meter cube. Abhishek sir, is the picture is visible? Is the
Yes,
picture
sir,
visible?
visible. Yes, yes.
Because I cannot see the slide, only means your desktop I cannot see, only I can see my desktop. So in that case I'm little
Yes, sir.
confused, is it visible or
No,
not?
currently we are in the slide types of PCM.
Right. So in the
Yes,
I'm discussing about that slide only.
yes,
In the slide
yes,
there is one graph. So okay.
yes, yes.
So in this case, I can say salt is having more enthalpy, means it can contain more amount of heat. So better the salt can utilize as a efficient energy storage material because it is having high possibility to hold the heat. But whereas you can see in the left side, extreme left side, there is one red color circle. You can say water salt eutectic. I think it's hopefully it is visible, that is having melting temperature also in the negative side, and also melting enthalpy in the range of 300 megajoule per meter cube. So the 1 meter cube volume of this eutectic salt, water salt eutectic, can store only 300 megajoule, whereas the salt, certain salt can hold 700 megajoule per meter cube. That means salt can store more amount of heat. So what we can correlate from this, if we want to store heat from the solar, we need less amount of salt, whereas the same amount of heat, if we want to store, we have to utilize more amount of paraffin wax or other material, those who are having less melting enthalpy. So these are the things, based on that we have to design the energy storage material or energy storage system. Later we will discuss this thing also, how can we find this melting enthalpy through the experiment. I'm going to give some brief introduction to calculate or to analyze this melting enthalpy. Okay. So from this slide, we are going to understand once again the principle of PCM or principle of phase change material, how the phase change material store the heat. I think you might aware about this thing, the sensible heat and latent heat. So in this case, I would like to say that in case of phase change material, as the name implies, phase change. Phase change means phase is going to change, either liquid to solid or solid to liquid. Only this heat, when the phase is changing, that heat only is required or we can utilize in case of PCM. So when the phase change occurs, in that time what heat is useful? Not the sensible heat, only the latent heat comes to the picture. So in short, I can say, in case of PCM or in the fundamental of principle, only the latent heat is to be utilized. There are certain other energy storage materials that utilize sensible heat also. Sensible heat is what? When the temperature of material is rising but phase is not changing, in that case the sensible heat comes to the picture. But when the temperature is constant and the phase is changing, that is the latent heat. As through one basic fundamental example, I wish to convey this message once again. While boiling of water, when we start boiling of water from normal temperature of household water like 25 degree, so when the boiling occurs at normal atmospheric pressure, what is the temperature? In that case, temperature is nearly 100 degree. So when we start boiling of water from 30 or whatever the room temperature, so let's consider 30 degree as a room temperature. From 30 to 100, the temperature will rise, but water will not convert its phase. Okay, so in this case, whatever amount of heat, how much amount of heat the water will store, that is considered as a sensible heat. But once the temperature will reach to the 100 degree, further if we will heat the water or we will continue the burn the fire, in that case the temperature will remain 100 degree, but the water will start vaporization. In that case, whatever amount of heat we are giving, that will consider as a latent heat. In the same manner, in the case of PCM, when we are giving heat to the phase change material or through some other medium like solar energy, whenever the solid PCM, for example, keep in mind paraffin wax or simply wax, it is in solid state. So when we are giving heat to the paraffin wax, it start melting at certain temperature. Generally, it occurs at 45 degree or 50 degree, 50 to I can say 40 to 60 degree. So in that case, when the PCM is start melting, it stores certain amount of heat. So that heat only is can be utilized for the energy storage application. I will tell you this thing in detail in next slide again. So these are the fundamental of phase change materials. So uh, in short, I can say phase change material utilize only the latent heat when the phase is changing and the temperature is remain constant. Now, limitation of PCM. In general, I'm not saying only for the organic, inorganic, all the PCM, three kind of PCM, organic, inorganic, and bioderived PCM, what I discussed earlier, all are having the major disadvantage, two major disadvantage: low thermal conductivity and leakage during phase change. Apart from these two, there are certain more disadvantage, that is supercooling, phase separation, volumetric extension, cost, corrosion, environment safety, and other things that we are not going to discuss, because these are disadvantage. Definitely we have to work for that, but the major disadvantage is low thermal conductivity and leakage. As from the name itself, you can see low thermal conductivity. In the figure also you can see it is having less tendency to transfer its heat. Very fundamentally, I can say, if the PCM is having stored energy, it's not able to transfer that stored energy efficiently. That is the low thermal conductivity. And also, if PCM is changing its phase, if you are keeping in certain container, definitely maybe uh, phase change will transfer its phase from solid to liquid. In that case, it can be leakage from somewhere. So this is one more thing that we have to encounter through the nanomaterial. How can we stop this leakage, and how can we improve the thermal conductivity? So these are the two major things. So as you can see, organic PCM having, or in short, you can see in the picture, the thermal conductivity range of phase change material from start from 0.1 and maximum it goes to 0.6 watt per meter Kelvin. 0.15 to zero point 0.6, that is the maximum range of thermal conductivity. You can correlate this thermal conductivity from the case of copper. Copper is having maximum thermal conductivity around 300-500 watt per meter Kelvin. But in this case, if you compare with the copper, you can see how low the thermal conductivity of the phase change material. Okay, so maybe you have certain doubt why we are focusing more in thermal conductivity, because if you see the literature, most of the research work is focusing on the thermal conductivity. Why we are focusing on thermal conductivity, that we will see in the next slide or some upcoming slide. So some required, as we have seen the disadvantage or some drawback of the PCM, now we will go for the required properties of PCM. What required properties? So in case of thermal properties, you can see high latent heat of fusion. As I already told you, a PCM which is having high latent heat or high heat of fusion, it means if it when it is changing the phase solid to liquid or liquid to solid, in that case it should store more amount of heat. That is the most important requirement for energy storage material. Also appropriate phase transition. I cannot say appropriate, based on the application. So you can see the household or domestic application needs temperature around 60 to 80 degree or 40 to 80 degree. But for industrial application, the temperature range is little higher, 200 or 400 degree. So where we are using that type of, based on the application, the phase transition temperature of the phase change material should be available. High thermal conductivity is the one important property of the phase change material, because if the phase change material is having high thermal conductivity, it will definitely store heat fast and also release the heat fast. When we need to store, it will immediately store the heat, and when we need to release that heat for any application, suppose in the daytime we want to store the heat from some solar collector, the solar collector will store absorb the heat, and it will transfer to the phase change material through some heat transfer fluid. In that case, if the thermal conductivity of the phase change material is high, it will immediately store the heat, or fast it will store the heat. But at night, when the solar energy is not there, but we have to utilize that heat for certain application, like we want to make house warm. In case of winter, the house is cold, and in that case, if you utilize the solar energy.
Sorry for the interruption, Dr. Manmohan. I am making him mute.
Okay, sir. Okay. Okay. So I was talking about the thermal conductivity. So if the thermal conductivity is high, material is stored already heat from the daytime, in the daytime through the solar collector, but that possesses certain heat. But if you want to utilize that heat to for any application, if the thermal conductivity is high, it will easily release the heat to the room or any application. Further we will discuss this thing also. So this is the one more property that we want. And thermal stability, thermal stability I can explain through one example. If you will heat the paraffin wax at very high temperature, or coconut oil is also one example of phase change material. In the winter time, you can see it is in solid state, and summer it is in liquid state. Definitely it is a phase change material. Certain time it is liquid, in certain temperature it is solid. So it is also one phase change material. So if you will heat the coconut oil at very high temperature, what will happen? It will evaporate. Directly take a pan and put the coconut oil in the pan and start the burner. In that case, it will start fume formation, and it will evaporate after certain time. So this is also one thermal stability is also one important application, important property. If we are utilizing certain phase change material at certain temperature, in that case the material should not degrade its property, as well as it should maintain the mass transfer will not take place. That is the thermal stability. Means at certain temperature, what mass we have taken to store the energy. Suppose we have taken 1 kg of paraffin wax as an energy storage material, and we are utilizing that material at 100 degrees centigrade. After certain cycle, heating cooling 100 cycle, then also the mass should be 1 kg. That is the thermal stability. So certain cycle, the mass should be remain constant. So these are the some thermal property, as well as physical property is also important. The small volume change, when the material takes place, changes its phase, so liquid to solid, the volume will reduce, and when the solid will become liquid, the volume will increase. In that case, expansion or contraction takes place. So this is on physical property. If PCM is changing its mass, large amount of changing its volume more than 30%. In solid state, the volume is suppose 1 meter cube, but in liquid state, the volume will become double. In that case, this is not desirable in case of thermal energy storage. Why? Because we have to design container, and if volume change is large, we have to design a big container. So we can consider this thing, but if the material is available in certain nature that is having small volume change property, that is desirable for thermal energy application. And also wide operating temperature range means uh, PCM not only PCM phase change temperature not only in 40 to 60. At certain application we need at 100 degree, at certain application we need at 200 degree also application. In that case, PCM should having wide operating range. So this is one more physical property. Low vapor pressure, that if vapor pressure is low, it will prevent the evaporation or mass loss. So that is one also one physical property. Also economical, as you know, is very common thing. Cost effectiveness is recyclability. These are some economical and practical consideration. Chemical property, it should be non-toxic, non-corrosive. Chemical stability, as I already told you, compatibility with container material, that should be not corrosive in nature. Chemical stability means if you are keeping the PCM in certain container, it should not react with the container material or whatever the auxiliary things we are utilizing in the system. It should be non-reactive with those things. Definitely non-toxic is the prime most important chemical property. It should be safety concern about the consumer as well as the industrial application. So these are the some required properties of the PCM. Now, the thing, what the title says, my title says the multifunctional PCM. So far we have discussed very fundamental things of the phase change material. Now the things multifunctionality. So you can see in the picture, the PCM was started in I can say discovered for application in 1990. This is the based on the Scopus database of the research publication. So they start on 1900 as a energy storage, thermal energy storage material. Later the application takes place. Building application has been come in 1979. Further the application for direct thermal application, like you can see in the picture, PCM is utilized on not only for the thermal application, it is utilized for life science also. Drug delivery application is also there. Photothermal application, greenhouse, the things greenhouse, I think better way. So greenhouse application is also there. You can see one person is wearing one jacket. In that jacket, phase change material has been incorporated so that in very cold climate, certain region where the temperature is -20, -40 degree, in that case, PCM material will store heat. When it is in the house, inside the house, the jacket will store heat, and the PCM will change its phase. Suppose in the house, the material is in liquid state or semi-liquid state. Once the person will wear the jacket and go outside, it will release heat, it will restrict the cold wind to the human body, and it will preserve from the cold climate or harsh climate. So this is one application. Thermoelectric application, this thing we'll discuss later also. This is just only the brief introduction of the application. Electromagnetic shielding, electromagnetic waves can be sealed through different, not the phase change material. Phase change material will work as a supporting medium, but
Yeah.
some nanomaterials. Yes, anyone ask any question?
No. Kindly
Okay,
continue.
okay, please. So electromagnetic shielding is also there. So in electromagnetic shielding, what the PCM helps? PCM helps as a supporting medium to support the certain nanomaterial that will makes as a shielding for electromagnetic waves. Like the recent development suggests that certain cloth has been designed in which the phase change material along with the nanoparticles has been attached. That cloth will shield the electromagnetic waves. So these are some applications. One more application I wish to explain here, that is a building application. In building application, what happens? Uh, the phase change material is filled in between the walls, glazings means the window sills. So the glass of the window, the two layers of the glass of the window has been filled with the PCM in between them, and it will restrict the cold coming outside. So when the cold is coming outside, it will absorb the cold wind and the transfer its phase, and it will prevent the inside person from the harsh climate. So these are some application of the phase change materials. So based on that, I have given the title multifunctional phase change materials. First of all, I will start the multifunctionality with the thermal energy storage. As I already frequently I have talked about the thermal energy. So you can see the left side picture. In this picture, if you are able to see, very cold climate. This is very old picture I got somewhere from the literature. Very old picture. In this picture, you can see the fire has been started with the wood or coal, and there is you can see the stones are used to heat the the fire has been used to heat up the stone. Why? Suppose in the night time the room has to be made hot, but in that time no one will take care about the fire, how the fire is taking place, how the fire is going on. So in that case, what we can do, in that case, the person who is standing there, who will heat the stones throughout the day, and he will go somewhere away in the night time. But once the stone will heat up properly, it will release heat slowly, and by the convection of the air, the hot air will go to the hall or room or building. So this is the first ancient application of thermal energy storage. In that case, the thermal energy storage has been taken or has been advantaged by the stones, not the material, any phase change material. So that is only the sensible heat storage. You can see in the right side picture, heat energy storage, thermal energy storage has been categorized in 4 different types. The first type is sensible heat storage. In that case, you can see, as I already told you, when the material is not changing its phase but storing heat, that is the sensible heat. So in that case, stone is a material that is not changing its phase, only taking the heat. So in such a way, it is a sensible heat storage material. But the latent heat is what? When the latent heat material is taking heat and changing its phase. So based on that, second category will come to the picture, latent heat storage material. That is further categorized in different categories: solid gas, solid to liquid, liquid to gas, and solid to gas. In all these 4 subcategories, you can see the material is changing its phase. So that's why latent heat storage. In further third category, you can see thermochemical energy storage. Thermochemical energy storage is what? When the chemical interaction is, chemical reactions are exothermic and endothermic in nature. So whenever certain material is reacted with some different material, it will release certain amount of heat, or it will need certain amount of heat to continue the chemical reaction. So in such a way, heat is involving in the reaction. So that is called a thermochemical energy storage. As well as the sorption heat storage is also one energy storage technology, but limited application. In that case, certain gas is absorbed by certain material, like what I did in my PhD also. The hydrogen is stored in metal hydride, certain material. When the hydrogen reacts or absorbed by certain material, it will release certain amount of heat. So in that case also, heat is taking place, heat transfer is taking place. So that also kind of energy storage process, that is called as sorption energy storage. So basically these are the category of thermal energy storage. So most of the case, or I think all in the all throughout this presentation, I will consider only the latent heat, that second one, not the first, second, first, third, and fourth. Only I am considering the latent heat energy storage. And also in this latent heat, only I will discuss solid, liquid, or liquid solid, not other like liquid gas or solid gas PCMs. So that was the first application, as you have seen, the thermal energy storage. This picture is only for the representation how the uh, thermal energy storage is applicable for building application or other one application. In the left side picture, you can see the PCM has been utilized to take heat from the solar, and further the heat has been utilized to run the turbine. So this is the application for phase change material. Why this needed to be designed? Why? Because in if you want to utilize the solar energy through uh, solar collector, concentrating solar collectors, or we want to circulate certain fluid to run the turbine, definitely it needs heat, but the heat is available only in the daytime. So in daytime there is no problem to run the turbine, because through solar collector, concentrating solar collector, that is able to create a temperature around 250 or 200 degrees centigrade. Definitely i- okay. So if a pipeline, you can see in the picture, if the in the pipeline, if any fluid is circulating, it will pass through the solar collector. The concentrating collector will make a fluid at a temperature of 200 degree. In that case, the fluid will change its phase, and it will become high pressure vapor, and it will go to the turbine, and it will rotate the turbine. So in that case, the daytime, it's fine, there is no problem. But when the night time, who will make the temperature, who will rise the temperature of this fluid to continue to maintain the continue operation of the turbine? In that case, energy storage will come to the picture. What we can do, we will store the heat in the daytime in the thermal energy storage material, or PCM. When the night time start, the thermal energy storage material will release heat automatically, and it will rise the temperature of the fluid. In such a way, the cycle will continue. So this is one of the example. Further, in the figure B, or right side, you can see, as we are in India, I think we do not need to make our house warm in any condition, except certain part of India. But most of the part of India, we do not need. But in certain region of the world, they need to heat our house. They need to heat their house, right? So in that case, you can see in the picture, there is a solar collector in the rooftop that will that will trap the heat in the daytime, and in certain material, that material nothing, only the thermal energy storage material, that will store the heat in the daytime. That time the system is only storing that. I generally use the word charging. So in that time, daytime the material will store the heat in the charging cycle. Once the sun set down, the energy storage material that store the heat, it will release heat and circulate through some heat transfer fluid, and it will make the house warm. This is the application of phase change material for thermal energy storage. Now there are certain more application. I will go little later. Now you can see the performance enhancement of thermal energy storage material. Now once again I will go to the back. As I already told you, we will discuss this thing later. So I told you thermal conductivity, the word I think you already listened. Thermal conductivity of the phase change material. I already said that thermal conductivity is the foremost important to efficient performance of the phase change material. It will easily absorb the heat, it will easily release the heat. So in that case, if we will, as I already told, the thermal conductivity is very low of phase change material. So if we want to increase the thermal conductivity, we have to adopt certain strategy through nanomaterial or through mechanical technique also. So if you will see in the left side figure, you can see there are certain techniques as a mechanical technique or material technique that will enhance the heat transfer or thermal conductivity of the phase change material. So that is, if someone from the mechanical background, they can understand little easy way. Fins, heat pipe, multiple PCM encapsulation. Also, some porous material we have to mix with the phase change material. And if you will go in detail, particularly for the nanomaterial, what type of nanomaterial that we should mix with the phase change material, you can see a lot of things we can add with the phase change material as a nanomaterial. That is 1D material, 2D material, metal organic framework, encapsulation of the phase change material, 3D material, carbon foam. These are the some material based techniques that will increase the thermal conductivity. So some mechanical techniques are also there. Some nanotechnology is also there. In mechanical techniques, what we are doing, we are not mixing anything with the phase change material. Only what we are doing, we are changing the arrangement of the system to increase the thermal performance, not increasing the thermal conductivity. We are not going to increase the thermal conductivity. We are increasing the performance through mechanical techniques. Like if we will increase the surface area of the material, definitely the heat transfer will increase. But in case of nanotechnology, what we are going to do, we are mixing certain nanoparticles or nanomaterials to the PCM that will increase the inherent property of the material, phase change material. So these are the some basic difference between the mechanical techniques and nanotechnology. But the objective of both the techniques are the same, to enhance the thermal performance of the material. Now, as I already mentioned this thing, my presentation is basically for the nanotechnology, not for the mechanical technology. So I am going a little deeper for the nanotechnology, how the nanotechnology can be introduced for the phase change material so that it will increase the thermal performance of the material. So as you can see, this is also one published article, and I have taken from there. The nanotechnology can be divided into four types, for particularly for the phase change material: 0D material, 1D material, 2D and 3D material. So these materials are need to be mixed with the phase change material so that the fundamental properties or what property we need, that can be increased. So the nanotechnology has been divided in two types. Left side you can see based on the geometry of the material or size of the material. Right side based on their uh, material category. So right side you can see the nanotechnology for the PCM has been divided in carbonic, ceramic, metallic and polymeric. That means these four category of materials need to be mixed based on the requirement, so that we can improve the thermal performance, and in short, not thermal performance, thermal conductivity. My major focus is on thermal conductivity. Both the things are same, you can see in the picture, but left side I have divided in their geometry or aspect ratio. The same thing, same material has been categorized based on the material. So carbonic material comes as a CNT, CNF. CNT is carbon nanotube, CNF is carbon nanofiber, graphene oxide, reduced graphene oxide, carbon foam, etc. So these are the certain carbon materials that we can mix in the nano form in the PCM. Further, ceramic material like aluminum oxide, titanium oxide, silicon carbide, zinc oxide, MgO, boron nitride, these kind of ceramic materials can be mixed in the phase change material, so that it will improve their thermal physical properties. Metallic material, this is the most common and extensively researched materials that has been done from last 20 years, I think, in the phase change material, that copper, gold, silver, nickel, aluminum, metal forms. This has been already mixed with the phase change material for improving of thermophysical properties. Like polymeric material is also kind of things, but these are not majorly used for thermal conductivity, but these are the used for encapsulation of phase change material. Encapsulation is what? When we have to preserve the phase change material from leakage, like capsule. Have you, I think all of you have been seen the capsule, what we are taking as a medicine. The capsule inside contains several medicines. In such a way, PCM is also been encapsulated in certain coating, that is a polymeric material. Through that we can encapsulate the phase change material, so that when the phase change material will takes place, will change its phase, it will not be having any liquid or any leakage problems. So these are the some functional fillers that can be mixed with the phase change material. And also these functional fillers having their distinct advantage, so that they will improve the thermal property. In maybe in next slide we can see, 1 minute. I will go back again. Let me check. Right, I think the slide need to be there. Okay, I will go back again. See, as I was telling that functional fillers, so 0D fillers, 1D, 2D and 3D fillers, you can see from the picture how these fillers can improve the thermophysical property or majorly thermal conductivity, what I am focusing. You can see 0D fillers. 0D fillers are what? Nanomaterials in the spherical form. Some basic example is copper oxide particles, gold particles, silver particles, carbon quantum dots, whatever the particles having spherical shape, I have considered as a 0D fillers. So 0D fillers are nothing. These are behaves like a thermal hotspot and provides a conduction network for the heat. You can see from the picture, if we are mixing these things in the phase change material, it will absorb the heat and provide a propagation path for the phase change, for the heat inside the phase change material. Similarly, 1D filler also, but 1D filler are more efficient as compared to 0D fillers, because it is having the structure like uh, tubes or like thread. So they are having more efficient to conduct the heat transfer. So these are similarly 2D and 3D fillers also. 3D fillers are like foam, sponge kind of thing. If a sponge kind of thing will absorb the phase change material, definitely the sponge is having more thermal conductivity than the phase change material. It will efficient transfer the heat in the filler inside the composite, and it will improve the thermal conductivity. You can see in the picture also, in case of fillers, the initial thermal conductivity of phase change material in the pure form, it was 0.3 watt per meter Kelvin. But when the expanded graphite has been introduced to the phase change material, the thermal conductivity has been raised to 6.5 watt per meter Kelvin, from 0.3 to 6.5. So these are the certain example or fundamental how the heat transfer has been improved in case of phase change materials. I think I should go back. Abhishek sir, how much time I have?
You can take your own time, Dr. Manmohan. No issue. Talk is very interactive, and even I'm getting feedback. Very informative session. Thank you, sir. And Mr. Suraj Kumar asked one question. Can you
Yes, sir.
provide some example of popular phase change materials used in various industries?
Definitely. So the most popular phase change material is paraffin wax. Even I am also working with this only, and most of the publication you can see even in industries also. But as per my knowledge, because I am not industry person, but what I have seen in academic research, the phase paraffin wax and ecocene, these are the most common example. But in industry, hopefully, based on the we cannot say any specific example, because the material depends on the application. If certain company is uh, designing application for 30 to 100 degree, in that case organic phase change material is can be taken. But if certain industry is designing for 300 to 600 degree, in that case definitely the hydrate salts can be utilized. So it is wrong to say that common example for any application, but based on application we have to choose the phase change material. But as per my knowledge, academic research is basically deal with the paraffin wax and stearic acid. These are the two most common phase change material. Uh, I hope the who has asked the question might satisfy. And also, if he want to talk later in the last, also we can discuss this thing.
Yes, definitely.
Uh, I was sorry for the inconvenience. Just a minute. Right. Right. It's little bit repetition of the slide, but some point need to discuss in this slide also. I think functional filler and PCM performance. What the functional filler does, as I have already told many times, the thermal conductivity, heat transfer, high latent heat. Apart from that, one important thing is photothermal conversion, that definitely I have to discuss. Photothermal conversion is what? Uh, I think this should be discussed more. Phase change material, if you want to store heat, there are two ways to store the heat. One is indirect way and one is direct way. Indirect way is what? I have to show with this example. See, in this figure, you can see left side figure, if you will see, left figure means figure A, bottom. There is one tank has been made, written by TES. Dr. Sharma, is it visible that tank TES written over there?
Yes.
In figure A, in the bottom side, there is one small tank with orange color written as TES. Is it visible, right?
Yes, visible.
Okay. So this is indirect way. If someone want to store the heat, he has to utilize solar collector. The solar collector will absorb heat, it will transfer heat to the heat transfer fluid, and it will go to the thermal energy storage material. This is indirect way. But when the direct way come to the picture, direct way means what? The phase change material itself store heat directly from the solar. There is no medium in between. That is the indirect way. In that case, this thing will come to the picture. Point number 1, 2, 3, 4, 5. Fifth point, photothermal conversion. Photothermal conversion is what? a certain nanomaterial that we have to mix with the phase change material, so that the phase change material itself get ready to store the heat. That means what? If you will keep the, I'm taking once again the same example, coconut oil. If we'll keep the coconut oil in the outside of the house in the direct sunlight, definitely it will store the heat. It will rise the temperature, it will melt, and after certain time the temperature will become more likely 30 to 40 degree. But what if you want to store the heat 60 degree? I think it is not possible to go 60 degree at certain condition. But now nanotechnology come to existence. If you will mix certain material, nanomaterial, to the phase change material, that are the capable to convert photon light. Photon is a nothing but bundle of light. Okay, so photon, that material, nanomaterial, what we have mixed in the phase change material, that will trap the photon, and that light automatically convert to heat. That is the photothermal material. That kind of material we have to mix with the phase change material, so that the phase change material itself able to store the heat without any medium, without any heat transfer fluid. So this is one of the important property that we have to improve in the phase change material. So this is also the recent research what going on to increase the photothermal conversion property of the phase change material. The other properties like thermal conductivity, latent heat, what I have discussed, this is also paramount important things that we have to consider while designing the thermal storage material. But when we are going to multifunctional application, in such case, I will show you one thing, then I will come back to the slide. Please give me one moment. One minute. Oh, like this. Is it visible? A person is standing skeleton. I think, are you able to see?
Yes, 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 visible.
Definitely. Okay.
Yes, sir.
So in that case, you can see right side bottom, there is one person wearing some gadgets and one cloth that's showing the heat. Okay. Therapy, some, have you seen that in some time we are getting some problem with our joints? Our relatives or our father mother, they are saying just put some oil and rub it and give some heat. In that case we are getting some relief from the pain, right? In the similar manner, the phase change material come to existence when we need thermal therapy. Thermal therapy means what? We have to take heat from solar, and if we are wearing certain kind of cloths, that cloths will absorb the heat, and it will distribute the heat throughout the body or particular location where we are feeling some problem. So in that case, PCM will store heat. But how? In that case, can you believe that we can arrange some heat transfer fluid solar collector in small place of body? Is it possible? Definitely no. In that case, we have to store heat directly in the phase change material. But how? Phase change material is not having that much property that it will store the heat or it will convert the light to the heat. In that case, we have to introduce certain nanomaterial. That material will what it will provide? It will improve the property of phase change material, so that the material will convert light to the heat. So that material, the fundamental material is CNT, carbon nanotube, that is having photothermal property. I'm going back once again. Mm, 1 minute. Right. Once again, please focus on 1, 2, 3, 4, 5. Fifth point, photothermal conversion. So what I was telling, the photothermal conversion of phase change material is not possible. Phase change material is not having that property. Whatever phase change material I have given example or given in brief, that material is not having property that can take heat and convert as a that can take light and convert as a heat. So to improve that property, we have to introduce certain nanomaterials. So CNT is having one material that is having a property. If you will mix the CNT in the phase change material, definitely it will improve the property of phase change material, so that it will take light and it will convert to the heat. The recent work is going with the material Maxine. The Maxine, MXENE, Maxine is a one latest material that is going in the field of photothermal conversion of phase change material. If you will mix the Maxine, that is a 2D material. Maxine is a 2D material, not a 1D material. If you will mix the Maxine in the phase change material, it will improve the photothermal conversion. Photothermal conversion means photon to thermal, means light to heat. So these are the application of functional filler in the phase change material. Also some other properties, also durability and reusability. Like durability means what? Phase change material, if you will repeat the thermal cycling, means it will heat, it will cool, heat cool, like cycle will takes place, definitely certain phase change material will lose their property or their flexibility. So in that case, certain nanomaterial, if you will mix with that, most common is CNT, it will improve the durability of the material. And other properties also, like customizable thermal property, means if certain material is having thermal conductivity or phase change temperature of 40 degree, if you will mix the thermal CNT, definitely the thermal conductivity and phase change temperature will change.
Sorry for the inconvenience. I'm making mute to a who has Banjeet Gope, kindly mute.
Okay, Abhishek sir, please tell me, because participants are also important their time. So exactly,
Yes,
I'm
yes.
not able to understand how much time is remaining. Please
Uh,
stop me whenever you feel it's over. Okay.
If it is possible, then kindly conclude in coming 15 minutes. But no issue. Means the
Okay.
topic is very interesting, and we are very thankful. You are means those who are even not aware about the PCM material. You are telling from fundamental to advanced applications. So really, a topic is very interesting, and we are very thankful.
Okay, sir. Thank you. So I think these are fundamental has been over, and application I will show you in brief. But before that, I wish to show something that I have done and I have feel in characterization. So in this slide, there are 4 slides. I will tell you. First slide is thermal characterization. Through that characterization, we are able to understand the thermal conductivity, latent heat property, and the mass degradation of the phase change material. In the four things we can understand from the thermal characterization. Phase transition temperature means at what temperature the phase change material will change its phase from solid to liquid, and again liquid to solid. That is the phase transition temperature. It possible only through the DSC. DSC is the one characterization technique, differential scanning calorimetry. Through that we can understand the melting temperature, the latent heat, how much latent heat it needs to change its phase, or it will release to change its phase from solid to liquid or liquid to solid. Thermal stability means at what temperature you can are you able to see the second figure? I think I will make it zoom. Is it
Yes,
visible,
yes,
second figure? Okay.
yes, yes, visible.
In this figure, if you will able to see, you are able to see weight percent is starting from 100. Is it visible, sir?
Yes, visible, visible. 100 to
Okay.
110. Yes.
Yes, yes. So this is the TGA, the TGA, thermogravity analysis. Okay, TGA. In that we are keeping the material. Suppose 1 gram material I am keeping in the instrument. That instrument is TGA, thermogravity analyzer. and I'm increasing the temperature, then as I already told you, uh, it should be maintain its mass, because means at certain operating temperature, if you are performing the application, the mass should be constant, the mass should not be degrade, or mass should not be loose. So in that case, suppose the mass was 100%, and I'm increasing the temperature. In the x-axis you can see I started from 50 degree, and I'm going further to rise the temperature 50, 100, 150. So you can see at certain temperature around 200 degree, the mass, initially the mass was at 100, but the mass suddenly come down, the graph is suddenly down. So in that case, the mass evaporation takes place. Okay, mass has been lost, 100 to sudden the graph has been down. So in that case, at what temperature the mass has been down? At 200 degrees. Suppose 200 degree means this phase change material can be applicable within 200 degree, not more than 200 degree. Why? Because after 200 degree, you have seen the mass has been down, mass has been evaporated somewhere in the atmosphere. So this is the TG analysis gives at what temperature we have to decide, at particular what temperature this material can be utilized. Are you able to understand, Dr. Sharma?
Yes, sir.
And
Yes, sir.
everyone?
Yes, sir. Yes.
Okay, I hope uh,
Sir,
I'm
if you don't mind,
able to explain.
yes, sir, if you don't mind, can you explain again this DSC and TGA?
Okay, once again, I will explain. First, I will start with DSC, then again, I will come back to the
Yes, sir.
TGA.
Yes.
So DSC is nothing. We are taking the sample in one device, that is a DSC device, differential scanning calorimetry. We are keeping the that material in the device, very small mass, 2 milligram mass of the phase change material needed for this application, only 2 mg, 2 to 20 mg we can keep. In that case, the liquid nitrogen will float in the device, and the plot, you can see the bottom plot and the top plot, there is a curve in the bottom and top. The curve will automatically given by the graph, by the machine. In that you can see onset is written as wait a moment, how it will go down, wait a moment, yeah. Now you can see onset written 50. There is certain software that gives the this all plot without much effort. So you can see 50.9, that is the melting starting temperature. Through this graph you can predict that the PCM will start melting at 50.9 degrees centigrade. Similarly, in the top side you can see that is written solidification 41.8. In that case, solidification will takes place at this temperature. Also, the area of the curve, in the bottom side you can see minus 86.68. This is the heat. 1 gram of material will release 86.68 joule per gram heat. Through that we can understand the latent heat capacity of the phase change material. Means how much amount of heat it needs or it release when the phase change will takes place. So this is the DSC, the middle one is TGA, and the third one is simply thermal conductivity results. That's not a big thing, only you have to do the calculation. It's not much complicated. But the in TGA center, once again I wish to say that uh, in TGA, we will start with 100% mass, whatever the mass, 1 mg, 2 mg, or 5 mg, that is considered as 100%, and the temperature is keep on increasing. In that case, once you will see the curve will sudden fall down. In that case, whenever the temperature whenever the percentage start from 100 to start decreasing, you can say mass transfer takes place. It means at that temperature, if we will restrict the application at particular that temperature, the mass will remain constant throughout the application. But if we will increase the temperature of the application, means we are using the material for 300 degree application, in that case mass will automatically lose. the material what you are going to use for particular application, it will no longer with you, it will automatically evaporate to the atmosphere. So this is the TGA analysis. um, Roughly I have given some idea, hopefully you will understand. So these are the thermal characterization. And optical and photothermal characterization, there is one apparatus known as uh, photothermal simulator. This apparatus is equal, it gives equivalent light as a sun, because in characterization, if you are characterize the material in real atmosphere or real time sun, the sun intensity is not constant, it will vary. But in that case you will not predict the actual performance. So in that case we have to use the simulator that will give exact similar light from the solar and constant radiation in the closed chamber. We will keep the material in that instrument, and it will give how the material is absorbing heat and how the temperature is changing. So this is some basic information of the photothermal characterization. Some structural analysis also can be done if you are mixing some nanomaterial to the phase change materials, and then you will perform the XRD, FTIR, Raman, this kind of experiment. You are able to understand what the chemical composition changing if you are mixing some other material in the phase change material. Like if you are mixing carbon nanotube in the phase change material like paraffin wax, what kind of chemical reaction, what kind of chemical bonding is taking place, that you can understand with this FTIR and Raman spectroscopy. So these are the some structural and morphological characterization. And chemical composition also you can understand, like if you are mixing certain amount of material like 1 weight% of CNT, if you are mixing with paraffin wax, this analysis will prove that how much percent of material you have mixed with paraffin wax, and their phase, how the material has been changed is crystal structure. So this kind of characterization needs for research article, I think. I think a lot of more things are remaining. I hope maybe I have to discuss this thing later. Anyway, I will close with some applications that I wish to show you in very brief. These are some application that we are going to develop and in underdevelop or something already developed. These are the literatures, and also I am working on the same thing. If you able to see right side top figure B, in that case I think someone outside of the city, and if they want electricity, in that case what they can do, they have to use some module that is based on PN junction module. So that PN junction module, what it will do, it will as we all knows that Seebeck and Peltier effect, one side hot temperature, one side cold temperature, then module will generate the electricity. So in that case PCM is taking place, PCM is filled one side and it will store heat and it will create the temperature difference. And through that module, thermoelectric module is different thing, it is not a part of PCM, it is a different module made with certain P type N type material, and it combines with PCM. The PCM will create temperature difference, and through that the electricity can be produced and can be used for certain small gadgets to charge the gadgets. This kind of application is going on in the research field. Also you can see this is the real type picture. This is not my research, is someone published research. In that case the PCM has been utilized to generate electricity, and they are using to create a light, so electricity to as shown as a outcome of the thermoelectric module. Lot of things. This building application, PCM can be utilized to fill in the building to store the heat, and further we can utilize to make the house warm. This is one application of phase change material. They have made some prototype also. and analyzed the temperature difference before PCM installation and after PCM installation. They made some 10 by 10 cubic meter house as a model and filled with the PCM in the walls and observed the temperature difference. Significant temperature difference has been uh, analyzed, and they have also done with the pure PCM and with the nano material mixed PCM. So significant difference has been analyzed with the pure PCM as well as with the nano material mixed PCM. Definitely nano mixed PCM has given the better performance. These are some research published. This some real-time application they have done with phase change material. Some picture, if you are able to see that some nano material in micro size or nano size, you can see they mix with the phase change material filled in the container and keep inside the concrete wall. So that concrete wall is surrounded by the PCM material filled in the steel container. That container, when the summertime, the heat will come from the outside of the building. The material will restrict the heat. How it will restrict? It will take the heat. It will melt in the daytime, and it will not giving a way to go inside the house. In such a way, house can be made cold. This is one application, and some recent and high level research are going on in this way, that nanotechnology based wearable device, so that we can utilize phase change material for thermal therapy. So these are the some recent advancement. These are some consideration of PCM materials for wearable device. I think this thing already I have discussed. Uh, Maybe these are very simple and common things you can understand by yourself. Some desalination also. Desalination is nothing. It's converting the salt water to the fresh uh, drinking water. In that case also, you can see daytime desalination is possible because daytime sunlight is available. But what if the sun is not available? In that time, the solar thermal energy material will store heat in the daytime, and immediately after the sunset it will start releasing the heat to the water. Then water will get evaporated, further condensed, and can be used as a fresh water. So these are also one domain of phase change material for desalination, to create a to generate a fresh water. Hopefully conclusion is nothing. Say, not this much big, I can say. uh, Enhance thermal conductivity, structural property, and photothermal conversion. If we will improve these things through certain nanotechnology, because lot of research work has been already done in the nanotechnology separately without PCM. What some people are doing, they are developing or synthesizing nanomaterials, but they are not including their material with phase change material. The same thing, if we will include the phase change nanomaterial in phase change material, definitely lot more application we can generate. I hope this is the only one conclusion I can say. Go for the literature, find out the nanomaterial and try to incorporate in the phase change material. Definitely the property will improve based on the material what you are choosing, and try to develop some application. So this is my conclusion. And future research, I already said, try to develop some application based on the literature. Hopefully this I have done. Thank you.
Thank you, Dr. Manmohan. Session was very wonderful, and you have told us about from the basic to advanced, and even the application part also. And those who are even those who don't know about the PCM, they can also understand by your informative session. Thank you very much. So may I request the participants? Yes, Banjit Gope, you want to ask some question? Banjit Gope, Nandini Krishna, Nandini Krishna.
Yes, I am here. Sir, thank you
Yes.
for your wonderful presentation. So actually we had a session on PCM in the last previous days. It was
yes.
application level, but your presentation gives the very depth knowledge about the PCM and its applications. Thank you very much, sir. Very grateful. Thank you.
Thank you, thank you.
Thank you, sir.
Sashi Jain, sir, are you here?
I am here, yeah.
Sir, how was the session, sir? Your feedback?
It was really nice. I was really listening to the words.
Yes, sir.
Nice session and really enjoyed it. Yeah.
Yes, yes, sir. Yes. Thank you, sir.
And
Sujit, sir? Sujit Verma, sir? Sridharra, sir?
Okay.
Yes.
Anyway,
So-
one thing I wish to convey that if anyone from the nanotechnology background, because I am not from the nanotechnology background, I studied this thing and based on that I have given this presentation. But after 1 year, I am coming back to the India. I hopefully I will come back. So if someone from nanotechnology, those who want to collaborate with me, definitely I am looking for such a person that can synthesize the nanomaterial, especially carbon material, so that I will include that material with phase change material, and definitely I have certain idea to develop some application. So hopefully through Dr. Sharma you can get my mail ID, and I am very happy to collaborate with such research person that they are doing with nanotechnology, because I am from the mechanical background. I don't know much about the nanotechnology. So this is my message. If someone interested, definitely I welcome to them.
Yes, in a current study, researchers are also using the char, and they are activated the carbon and they are using in phase change material. So
Right.
there are a lot of scope is there. So I request all the participants to go through this recorded session. Also, I will share you. And if you have any question, you can ask. Later on also you can ask. We are working in a team, and you are open to ask questions. So Dr. Manmohan, there are a lot of comments are there for you. Thank you, sir, for your informative talk. Excellent presentation, very informative session. So all have very enjoyed. Even I don't know how we have passed, but we are just we are going to complete 2 hours. But
Oh, sorry for that.
no,
But
no, no, no,
I was
not sorry.
planned.
We have, yes, yes.
I was planned little more in depth, but I think due to time constraint, I have not given little. Well, I was planned, but anyway, next session or next FDP, hopefully Dr. Sharma will get another FDP. Then I will go.
Yes, yes.
Definitely.
Sure, sure. No, no, means
We will also try
yes,
to
sir.
rope in
Sure.
your expertise.
Yes, sir. Yes, sir.
Anna? Yeah.
Yes, sir. Yes, sir. Thank you, sir.
Very nice. Great.
Okay.
Great
So-
efforts by all of you.
Yes, sir.
Thank you.
So, and thank you very much, sir, to you all. You all are working from morning to evening to college, and
Yeah.
after that you are making sessions so interactive. So I am thanks to all the participants, and do not worry for anything. So thank you very much. Thank you to the speaker, and thank you very much to all the
And
participants.
also thank
Thank
you
you.
for all the guys, those who have given extra 30 minutes in this time, busy schedule.
Yes, now it is a dinner time. Then also,
Yes,
and
yes.
for you also, Dr. Manmohan, I think now they are 1 o'clock in
Yes,
as per
yes,
your
1
time.
o'clock.
Night
Yes,
1
yes.
o'clock, you are sitting here, and in such a energetic level you have discussed, and you have told us about phase change material, its application. Really, I'm thankful, and thank you very much.
Thank you, sir.
So
Great.
can I close the meeting, or anyone want to ask some question? Ajay Bhaumik.
Sir, this is a very excellent session that I'm getting. Today is also very excellent, sir. Really thank you,
Yes,
sir.
yes.
But
Yes, yes.
another technical question that I'm asking you. Tomorrow at what time it will start, and when the validation session will be start?
Sir, I will share all those information in the group, although, but I know that some university or colleges Saturday is working, so I have requested to AICT. So tomorrow we will have 2 sessions only, as usual, like today's 6 to 7:30 one session, and 7:30 to 9 o'clock second session. And we will conduct the last session and test on Monday. All this information I will post in the group also. but here whoever are available, so for them this is the information. Tomorrow we do not have test. Monday we will have test, and each and every information I will share in the group also.
Thank you, sir. That was the question. Okay, thanks a lot, sir.
Yes, sir. Yes, sir.
Sir, really, it's a very good session that you are conducting all through the days. And today, sir, Mohan sir, what he is stated, he is really outstanding. So many new information that we gathered. It's too good. Thank you, sir. Thank you all of you, sir.
And sir, even after this faculty development program also, we are always open, and we always believe that to disseminate the knowledge. So we are always open, and do not worry about the test and certificate and everything. You all have made this event very successful. So you all will get certificate. So Monday we will keep test, sir.
Sure, sir. Thanks a lot, sir. Thanks a lot, sir.
Thank you, sir. So Dr. Murli, please stop the recording. Then we will close the meeting.
Good night, all.
Thank you. Thank you, Sachi, sir.
Thank you, sir.
Thank you, Dr. Manmohan. It's late night.